This is the second lecture from Chapter 14 over chemical equilibrium, and this chapter will cover how to calculate actual values for the equilibrium constant, how to be able to tell if you're at equilibrium or not, and in which direction you need to proceed to reach equilibrium, and finally, what happens if you disturb an equilibrium. You'll learn that a system will always do everything it can to return to a state of equilibrium, which is the lowest energy position. So the easiest type of problem when calculating K, the equilibrium constant, is to simply be given the equilibrium concentrations of reactants and products and then plug them into your expression for K. So take a look at the most basic type of problem. And take the time here to actually look what's going on in this slide, because sometimes it's hard to imagine. If somebody tells you that the equilibrium constant K is a constant, but then also tells you, so here, let's look at the equilibrium constant for the reaction shown at the top of the page. Okay, so products over reactants raised to the whatever the coefficient is in front of them. So take a look at this, and if I told you, okay, the equilibrium constant at 445 degrees is 50, and that means that regardless of your starting conditions for a reaction, as long as the temperature is at 445, the ratio of products to reactants will always remain at 50. But there are more than one set of concentrations that will give you this equilibrium constant. So let's look at a couple of these just so you can kind of wrap your head around this constant or concept. So here are the reactants. So let's imagine we start, and this is the most typical scenario. Let's imagine we start with equal amounts of the reactants and no product. That's a typical scenario. And so the equilibrium concentrations of all of them are shown here so that when you plug into the equilibrium expression, you get a K value of 50. So now, what if we start that same reaction with only product? What will happen? Well, in this case, the reverse reaction will be the first thing that picks up. But look at at equilibrium, what the concentrations are. They're different. Okay, they're different than if we were to start with only reactant. However, when we plug the equilibrium concentrations into the expression for equilibrium, we get the same equilibrium constant. And that will always be the case regardless of how much reactant and product we start with, as long as we're at this set temperature. Remember, the only factor that will change the value of the equilibrium constant is temperature. Nothing else will. And so the rest of the trials are just showing you that you can have a variety, any initial concentration of reactants and products, and end up with an equilibrium product to reactant ratio that's still 50. So I just think that's kind of fascinating. I love this slide because it gets that concept across pretty clearly. Now, if you were a chemist following the progress of a reaction in the lab and you wanted to know whether or not it had reached equilibrium, how can you tell? What can you do? Well, you can measure, if you have an instrument that allows you to measure the concentration of reactants and products, you can go ahead and plug the concentrations you have at any point in time into the expression for K and see if you get what you're supposed to get for the equilibrium constant. So what we call this is Q, the reaction quotient. And Q is the same as K as far as the mathematical expression. So Q is products over reactants, just like K is, okay, raised to whatever the coefficient is, so they're raised to some power. But Q is the concentrations are taken at any point in time. So it's possible for Q to equal K sometimes, but most of the time Q will not equal K. And Q is just a measure chemists use to tell whether or not they're at equilibrium. So let's look at a couple of problems dealing with that. So just to set the stage for you, let's look at our generic reaction again. And let's say that I'm carrying that reaction out in the lab and I want to know if I'm at equilibrium. So I'm going to plug all the concentrations I have into the equation for Q/K and see what the value is. And let's say that I end up with way more product than I'm supposed to have at equilibrium. What will happen then? If I have too much product at the current time, that'll make Q very large, right? If you have too much product in the numerator, Q is large. So I might end up with a scenario where Q is greater than K, okay? Or let's imagine that I had a ton of reactant left. The reaction hadn't proceeded very far. So if I have way too much reactant than I'm supposed to for an equilibrium condition, that'll make Q very small, okay? So if you have a large denominator, the value is going to be small. So there will be other cases where Q is much less than K. And depending on the relative position of Q, it tells you which direction your reaction needs to go to reach equilibrium. As I said before, there will be situations where Q will equal K, and the chemist will go, yay, I'm in equilibrium. So that is a possibility. More often than not, Q will not equal K, and the chemist then has to be able to analyze the situation and determine in which direction a reaction needs to proceed to reach equilibrium. So let's first look at if Q is greater than K. Remember, what does that mean? If Q is larger than it needs to be, that means you have too much product. Remember, product is in the numerator of the expression. So if the value is too big, you have too much in the numerator, which is too much product. If, on the other hand, Q, the reaction quotient, is less than K, if Q is too small, that means your denominator has gotten too large. And what's in the denominator? It's reactant. Okay? So too much reactant. Another way of saying that is not enough product. Too much reactant is the same thing as saying not enough product. All right? And that means if you don't have enough product, that means the reaction must shift to the right and make more product. So if you have your little reaction here and you don't have enough product, we say the reaction must shift to the right to reach equilibrium. This slide is a nice little mnemonic you can use. If you have a hard time dealing with the less than greater than Q versus K, and plenty of people do, this is just kind of a slick little way to get a quick answer. So if you imagine a number line, which everybody has worked with, and let's say your actual equilibrium value is, your K value is 0.19, and let's say you plug in all the concentrations you have at the current time and you get a Q value of 4.2. So K does not equal Q in this case, so you're not at equilibrium, but let's say the question says, which direction does a reaction need to shift to reach equilibrium? And you have a little bit of trouble with that rationalization. It will always work if you place them on a number line in the right positions. You can see here that in order for Q to reach K, it needs to go left. And so you can apply that to your reaction. If you have a reaction, you could say that if Q is greater than K, and if these signs mix you up, just write out greater than. If Q is greater than K, the reaction will need to shift left to reach equilibrium. So that number is an easy little trick to use also. Here's a slide that will allow you to practice. This is an important skill. If you haven't already picked that up, it's an important concept to understand. And so just for practice, let's look at this reaction. That's the conversion of nitrogen dioxide. Oh, here go the dogs. Oh, maybe not. Okay, conversion of nitrogen dioxide to dinitrogen tetroxide. Here's the equilibrium expression. And the equilibrium constant at this particular temperature we're talking about is 0.45. And so let's say that you were in the lab running a number of experiments. And what I would do is I would cover up this entire right column and see if you can make these predictions on your own. So you can put the video on pause and cover that up if you want, but I'm going to walk you through a couple of them at this point. So first of all, obviously, you're never at equilibrium if you have made no product. So anytime the product concentration is 0, plugging 0 into any ratio, you're clearly going to get Q is 0. And so let's compare it to K. So for experiment 1, Q is 0 and K is 0.45. That means that Q is less than K. So which way does the reaction need to proceed? So I'll do it both the rational way, the logic way, and then the number line way. So if Q is less than K, that means that the numerator is too small, right? That's what makes something small. And what's in the numerator? Okay, the numerator is small. What's in the numerator? The products. So you have not enough product if Q is too small. So what do you do to make more product? You shift right, okay? So if you were to do that on a number line, we will do that now. Here's my number line, and I'm going to put K up here first. K equals 0.45, and then my value for Q. And for that first experiment, Q was 0, okay? So remember that you always want to start with Q, because that's the value you're starting with, and you want to arrive at K. K is your ultimate destination. So how do I get from Q to K? I have to shift right. So again, if that logic reasoning that I did on the last slide doesn't work for you, use the number line. So you would then answer the reaction must shift to the right to reach equilibrium. This slide is just going one by one over each of the experiments presented on 2 slides ago. So again, the first thing you do if you're asked to determine whether or not a reaction is at equilibrium, you plug in the concentrations of products over reactants in the expression for Q. You determine whether Q is less than K, equal to K, or greater than K, and then determine which direction the reaction must shift in order to reach equilibrium. And I strongly recommend practicing a few of these. Here's a typical problem, one that you, I'm sure, will see on your upcoming quiz as well as your test. And so go ahead and see if you can determine the answer to this completely on your own, and then I will go over the answer on the next slide. Just to get you started, I want to just tell you the order of things you need to do. The first thing you want to do is write your expression for Q, and remember, that's just like the expression for equilibrium constant. So it's concentration of products raised to whatever coefficient they may have in front of them. So here are your products. Remember to put a cubed for the concentration of hydrogen over concentration of reactants. Remember that if any reactants and products are pure liquids or solids, they get left out of the expression for equilibrium in Q. But pay attention here. This H2O is in the gas phase, not the liquid phase, so it gets included in the expression for K and Q. Okay, it's only when it's in the liquid phase. So anything that's gas or aqueous, those are typically what you'll run into, do in fact get included in the expressions. So now they're telling you the concentrations. You just plug those in, determine whether Q is greater than or less than K, and then predict whether or not the reaction is already at equilibrium or whether it needs to shift to the right or to the left to reach equilibrium. Well, assuming you did your math right and assuming I did my math right, You can see here that Q is greater than K, so you should have gotten a value for Q of 20. The value for K is only 5, so Q is greater than K, which means the numerator or the products are too large, or too high of a concentration of product. So if that's the case, which way will a reaction shift to get rid of some of the product? There's too much product. So a reaction will shift left. And so that is the correct answer. Now we're going to start on a very, very important concept in equilibrium. And you have an entire lab over this concept too. So it's a very important one to understand. And it is called Le Chatelier's. So, just as a brief introduction, if you have a reaction that's already at equilibrium and you disturb it, and there are a number of ways to disturb an equilibrium, you can disturb it by changing the concentration of one of the reactants or products. So you could dump an extra product, you could dump an extra reactant, or you could remove a reactant or product. Anything that changes the concentration will temporarily disturb an equilibrium. You could also change the temperature, and that would also temporarily disturb an equilibrium. Or if you have gases present, you could change the pressure, which would also temporarily disturb your equilibrium. So what Le Chatelier's principle says is that if you disturb an equilibrium, the reaction system will adjust until equilibrium is restored. So we're going to talk about all the different ways that can happen, but that's what Le Chatelier says, is that the reaction system will adjust until equilibrium is restored. And this is just my comic relief as I'm doing boring PowerPoints. I have to find little comics here and there. All right, as I said earlier, the 3 ways to disturb an equilibrium: temperature, pressure, only if there's a gas, or concentration. Remember, and I probably sound like a broken record in this case, but the only way to change the volume of the equilibrium constant itself is by changing temperature. So if you change concentration or pressure or anything other than temperature, we can talk about a reaction system shifting left or right, but in all those cases, K does not change. The value of K will remain constant unless you change temperature. Let's talk about changing concentration first of all. So let's look at a generic reaction, and let's imagine that we added extra concentration on the reactant. So I dump in, I've got equilibrium established, I dump in extra A. What's going to happen? Well, there's too much reactant, so what can this reaction system do to use up that extra reactant that I just dumped in? The only thing it can do to use it up is to shift to the right. And that's exactly what it'll do, and that's what you say. If extra reactant is added, the reaction will shift to the right to consume it and reestablish equilibrium. So let's imagine instead of adding extra reactant that I add extra product. So temporarily the concentration of product goes up. What can this reaction system do to use up that extra product? It can shift to the left, because by shifting to the left, these products combine to reform reactant. And by doing so, by shifting to the left, equilibrium can be reestablished. Now, there is another way to disturb an equilibrium by adjusting concentrations. Not only can you add reactant or product, you can remove a reactant or product. So let's imagine that I remove some product. If I remove some of C or D, that means we're going to have a deficiency, not enough product. So again, what can this reaction system do to reform the product that's been removed? It will shift to the right. Okay? And likewise, if I remove reactant, if I in the reaction vessel and take out some of the reactant that's sitting there in equilibrium, the reaction system will adjust by shifting to the left. So the bottom line is the reaction system tries to undo whatever you have done to disturb the equilibrium. So if you add reactant, it tries to get rid of the extra reactant. If you add product, it tries to get rid of the extra product, etc. I always include this slide about the Haber process, which is one of the most common industrial chemical processes used, and it's how ammonia is made in industry. So it's used a ton, and it's kind of slick. Chemists use the principle of Le Chatelier's principle to maximize their yield. So they have this vessel, and as ammonia is formed, they set up the vessel to remove the ammonia as it's formed. So they're constantly disturbing the equilibrium. So as they remove ammonia, what happens? The reaction system the equilibrium gets disturbed, and in an attempt to try to replace the product that is being removed, it makes more and more product. Okay, so it keeps shifting to the right to adjust for the disturbing of taking out the ammonia. And by doing that, chemists maximize the yield. They make more and more ammonia, and they get more bang for their buck. And so you really don't have to know this reaction vessel. I just think it's cool. So you have, you put your reactants in here. It's all gases. Everything is gas in this. You feed your gases in here. They get heated up, which accelerates the speed of the reaction. You've got a catalyst. So ammonia is formed in this side of the reaction vessel, but then they have an outlet at the bottom, and they pull out the ammonia, and so that just drives the reaction more and more and more. So pretty slick. They use Le Chatelier's principle to maximize their yield. Go ahead and give it a try yourself. Look at the reaction I've given you here and see if you can figure out what will happen, which way this reaction will shift if we increase the partial pressure of SO3. Now remember that in order to have pressure to have any effect at all, we have to have at least one gas in a chemical reaction, and we do, so we're okay. And the answer is an increase in reactant will cause the reaction system to shift to the right because it's trying to consume the extra reactant that you just added. So hopefully you got that. Dealing with changes in volume can be a little bit trickier, so you'll probably have to pay a bit more attention in this example. A volume change will, again, only affect equilibrium when you have gases present. But let's look at what happens. When we're changing volume, we're really changing pressure. So look at this vessel here in the figure. What happens when we decrease the volume? When you decrease volume, you increase pressure, okay? Makes total sense, right? You're combining all those little molecules to smaller and smaller space, and they're colliding much more frequently with the walls of the container, it causing more pressure. So decrease volume, increase pressure. And so how is a reaction system at equilibrium going to respond if you increase pressure or decrease volume? Since you are adding more pressure than the system is used to, it is going to do everything it can to try to reduce pressure. Remember, Le Chatelier says that a system will try to undo whatever you've done. So it is going to try to find a way to reduce the pressure. How does a reaction system reduce pressure? Well, let's look at that. Let's look at each side of this reaction in isolation at first. On the reactant side, you have 2 molecules of gas. Remember, pressure comes from collisions of gas molecules. On the product side, you have 3 molecules of gas. So just if you could isolate each side of that equation, what is contributing more to the pressure of this system, the reactants or products? It would be the products because there are more molecules of gas undergoing more collisions. And so if you increased the pressure of this entire reaction system, which way would it shift to try to alleviate that increased pressure or reduce the increased pressure? It's going to shift left to reduce pressure, because by doing so, if it shifts left, it has fewer gas molecules and therefore less pressure. So let's check this out. Again, let's go in the other direction. If we increase the volume, what happens to pressure? If you give molecules a much greater space to roam around in, you increase the volume, you're going to decrease pressure. And so which way will this reaction system shift if you have decreased the pressure? It's going to try to undo what you did, so it's going to try to increase pressure. How does it do that? It shifts to the right, where there are more gas molecules. And for the same reason, if you decrease the volume or increase the pressure, it's going to shift to the side that tries to undo that increase. It's going to try to decrease pressure, and that's shifting to the left where there are fewer gas molecules. So if all my chicken scratchings on the last page confused you, here's a nice, neat, trim version of the explanations you can use. And finally, if we change the pressure of a system, not by adding more reactant or more product, by adding an inert gas. What does inert mean? Non-reactive. It means it does not participate in this reaction. So we could just add something like, let's imagine a noble gas. So we just pumped in neon to this system. It doesn't react with anything, but by doing so, we increase the total pressure. Is that going to have any effect? No. There's no interaction between an inert gas and the reactants or products. Therefore, even though the total pressure is increased, the individual partial pressures of the reactant gases are not changed. So that does not shift the equilibrium. I used to have a really hard time wrapping my head around this, and until I really understood gases, I continued to have a hard time. So don't feel bad if that doesn't make a lot of sense to you, because you haven't learned a lot about the behavior of gases yet. All right, so we've talked about changes disturbing an equilibrium by changing concentrations, changing pressure, changing volume, and now finally we're going to talk about disturbing an equilibrium by changing the temperature. Remember that changing temperature also changes the value of K. So this one may be the trickiest one to understand. We'll see. All right, so in order to determine which way a reaction system will shift when we change temperature, we first have to know whether the reaction is exothermic, which means it lets off heat, or endothermic. And I want to remind you or show you how chemists show that a reaction is endothermic or exothermic, besides giving you numbers. So let's look at these generic reactions. If a reaction is exothermic, we show heat as a product. Remember, exothermic means a system is giving off or producing heat. So we treat heat as a product in an exothermic reaction. It's being given off or produced. If, on the other hand, a reaction is endothermic, that means it requires heat in order to produce product. In that case, we're going to treat heat as a reactant. So that's important to know. That'll really help you deal with Le Chatelier problems dealing with temperature changes. It's also important to remember, because in most cases, chemists will not write a reaction out showing heat as a product or reactant. So it's important to remember the symbols used by chemists. If it's an exothermic reaction, there will be a negative sign in front of the heat of reaction, or delta H, enthalpy of reaction. And if it is an endothermic reaction, if heat is a reactant, the delta H value will be positive. So I'll just make up a value here. Okay. So it'll be positive if it's endo. So you need to remember those symbols also. Let's look at an endothermic reaction first, which means I'm going to treat heat as a reactant. This is endothermic. Okay, we'll make it very simple. And so if I add heat, if I increase the heat, let's say this reaction is at equilibrium, and then I come in and I increase the heat, just treat it like you would treat if you increase the concentration of any reactant. Le Chatelier says that it is going to try to undo whatever has been done to disturb the equilibrium. So Le Chatelier says that it's going to try to decrease the extra heat I just added. How does it do that? It shifts away from the heat. It shifts right. Okay? Because by shifting right, it consumes that extra heat I've added. So for an endothermic reaction, if I add heat, you may want to jot this down, it's going to shift right. If I have an endothermic reaction and I have removed heat, so if I decrease the heat or remove it or cool an endothermic reaction, what's going to happen? Then it will shift left to try to replace the heat that I've removed. So if it's an endothermic, let's make a summary here. If it's an endothermic reaction and I increase heat, it's going to shift right. If I decrease heat or cool it, it's going to shift left. And it's going to be just the opposite for an exothermic reaction, which I'll show you. So here's an exothermic reaction. Remember that heat is treated as a product in an exothermic reaction. All right, so now in an exothermic reaction, if I increase heat, if I heat it up, in order to get rid of that heat, Le Chatelier says it's going to shift left. If I remove heat or cool it down, and it's an exothermic reaction, it will shift right. So, summary for exothermic reactions. If I add heat to an exothermic reaction, it's going to shift left. If I remove heat for an exothermic reaction, if I cool it, it's going to shift right. All right, so we only have 2 more slides left. I mentioned before that changing temperature also changes the value for the equilibrium constant itself, and so you need to be able to deal with that. So let's look at an exothermic reaction. Remember, the equilibrium constant is products over reactants. If we're dealing with an exothermic reaction, we're treating heat as a product. So if you have an exothermic reaction and you increase heat, it's going to shift to the left. What is that going to do to K if a reaction shifts to the left? You're going to make less product if it's shifting to the left, which means K will decrease. So in quick summary, if you have an exothermic reaction and you add heat, K will decrease. So you want to make a note of all these things and make sure you understand them, but also make sure you remember them. Now let's look at an endothermic reaction. That is, we treat heat as a reactant. And what happens if we increase temperature in an endothermic reaction? If we increase temperature, it's going to shift to the right. That means it's going to make more product. And what is that going to do to K? So K will, if we make more product, the numerator increases and K will increase. So you need to go through all these scenarios of increasing temperature, decreasing temperature for an endothermic and an exothermic reaction. Finally, a catalyst, which we know speeds up a reaction, has no effect on the equilibrium constant at all because the catalyst speeds up the forward reaction and the reverse reaction. So net, it has no effect on the equilibrium constant. That's it for this lecture. And the next one gets a little dicey. We get into something called ice tables and calculating the equilibrium constant when you don't know the concentrations at equilibrium. So that's a little bit more math in the next one. But that's it for this.